Let's begin. We will continue where we left off last time, which was the polynomial interpolants. We tried it out on this big data set and argued that it's a bad idea. High order polynomials are bad. They have a lot of roots. They're going to become oscillatory, especially at the boundaries. They're going to change sign, and then you're going to get unphysical, unbounded values at the endpoints. So they are a bad idea. And frankly, any polynomial that is greater than order 2 or 3 is going to be problematic. So then how can you fit a polynomial of order 3, which only has 4 parameters, a0, right, plus a1x, plus a2x squared, plus a3x cubed. So it has 4 unknowns, to a set of data that has 400 data points. You have more data than there are unknowns. So in that case, what we do local cubic polynomials or local quadratic polynomials. So you focus on 3 or 4 points at a time, and then fit a polynomial, a third or second order polynomial in those. So in that, one of the most popular ones are cubic splines. And cubic splines, they follow a cubic polynomial, and they fit a cubic between 2 points. That's a hard ask, because for a cubic, you have 1, 2, 3, 4 unknown coefficients. To obtain the conditions on those coefficients, we set conditions on the slopes and the derivatives, etc., at the endpoints. So we can figure this out, and we can Python does that for you very neatly. We can do the derivation by hand. We're not going to do that here in this class. I just want to show you the method. Cubic splines are the best type of interpolant you can get. They give you very smooth interpolants for data. They are stable. They rarely go out of bounds or have zeros or oscillate at the endpoints. They are very highly desirable. So the way to get this is you go into from scipy.interpolate, and you import the cubic spline class to create a cubic spline interpolant. Now remember, internally, what Python is trying to do is just like the interp1d is trying to put a straight line between every pair of points. And internally, Python has to figure out which straight line to choose when you're trying to interpolate a certain data point. So it has like an internal database where it needs to store all of those straight lines. Same thing for cubic splines. Between every pair of points, there's a cubic polynomial that it needs to store somewhere so that you can get the evaluation done correctly. So if you want to interpolate at this point here, it has to pick this cubic spline. If you want to interpolate at this point here, it has to pick this cubic spline. So it does that internally simply by applying the cubic spline class to the input x data and the input y data. So x input and y input, those are independent dependent variable. And you store that. That's kind of the classic way of applying this. You store that in a variable. Let's call it CS for cubic spline. And then from here onwards, you simply take CS and apply it to an array, to a single value, to interpolate data in between your input data. Right? So, and that returns a single value or an array of values. So let's go ahead and try this with the density temperature data set, which we should still have in our Jupyter notebook, hopefully. Let's see. If you can grab your Jupyter notebooks. So we were doing this in interpolation. Okay. And I will move my slides as well, so you remember. So go ahead and try to implement this on the data that we had. So let's remember our data. We imported this, etc. That was the input data. So xi was the input temperature, and yi was the input density. And when we plotted this data, we had this plot. This is the input data. And if you remember, we had this polynomial here. So finally here, we're going to do a cubic spline. cubic splines. And let's import cubic splines from scipy.interpolate. So we do from scipy.interpolate import cubic spline, right? So that's what this is telling us. And then we simply apply, create a variable, CS, and that's cubic spline. And the signature for cubic spline, it takes X data and Y data. So we will give it simply XI and YI. And if that succeeds, it's just going to give us, it's just going to succeed if you print CS is going to be something. It's going to be an object, an internal Python object of type scipy.interpolate cubic spline. So it contains a lot of information. What you need to know is that you can apply CS to any point here, and you can recover a value. So let's say 412, CS 412, and it's just going to give you a value, and that is going to be the density at that temperature. The best thing to do is then to plot this. So we're going to plot cubic spline. So you remember here we had temporary points, this temp points. I think it's still valid. So we can plot again, plt.plot temp points. And I'm going to apply CS on temp points. And I'm going to do this just a dash dot. And when you plot this, you get this really nice smooth curve, okay, because it's doing a cubic spline between each pair of points. You can plot the original data on it, plt.plot, and I'm going to put xi, yi, and I'm just going to make them into black circles. So that's the original data. You see there's a cubic in between each pair of points, as opposed to a straight line or anything else. Now, the cubic might have a 0 coefficient on the cubic term, so it could be a quadratic. Or it could be a straight line if the coefficients on the cubic term and the quadratic term are 0, right? It could be any one of those, but it's a nice smooth, it doesn't, nice and smooth, doesn't oscillate, doesn't cause unphysical answers. Cubic splines are the way to go. And that's it for interpolation. I'll give you an example of 2D interpolation, but I'll leave it up to you to play with that. If you're done with this now, let's put it here. Oh, okay. So let's come back here. You can also do 2, 3, 4, any higher dimensional interpolation. But you might say, well, when are we more than 3 dimensions? Well, if you have density, function of temperature, pressure, viscosity, other properties in the flow, each one of those is a dimension, right? So here's a 2-dimensional example, specific volume, which is the inverse of the density, how many cubic meters you can pack in a kilogram of material, as a function of temperature and pressure. So this is 2-dimensional data. And then you have, combinations of temperatures and pressures, and you get different specific volumes. And then you might ask, okay, I want the specific volume at a temperature of 175 and a pressure of 0.75 bar. What do you do here? We do linear interpolation between these 4 points. Python can do all of that for you. I have the formula here for you if you want to know how it's derived, but it's not required. I just put it here because I know you are, insatiable for math. You love the math. So this is what it wants to do. But for 2D interpolation in Python, you import from some scipy.interpolate, you import interp2d. So interp2d takes 2-dimensional data, xi, yi, those are the independent variables, so temperature and pressure, for example. Zi is your response, or the quantity of interest, which is the dependent variable, in this case, specific volume for the example. And there's a method, so we'll talk about the method in a second. So same as we did with cubic splines, you apply the interp2d on the data, it gives you an object, call it F2D, so function 2D, and then you give it any combination of values, of new values for x and y, and it's going to give you a new value for z. Method here, you can use linear interpolation, but you can do also cubic and quintic interpolation on the two-dimensional data. It's really great. It gives you cleaner and smoother surfaces for your interpolation. Okay, so you can do this. I have an example here for you that you can just program in your code and see what's going on. So this is an example where we have a temperature distribution on a plate, heat distribution measured by temperature on a two-dimensional plate, and you just have temperatures at these discrete intervals here. What if you want the temperature in here or in between or here or at any point in between? So with 2D interpolation, you can turn this into this. Okay? Be careful, you're not generating new information. Okay? You're not generating new information. You are just interpolating existing information. So this plot does not have any additional information than this plot. Okay? Don't think that, even if it looks smoother, it was derived from this plot. So it's not creating new info, it's just trying to interpolate what existing info you have here to make it a little smoother. But it's not new information. So you can try this. This is the code here, very simple and quick and easy. All right, let's switch now to the other type of curve fitting. So we said interpolation was when you have nice, clean, one-to-one data. Yes? Yes?
I'm a little confused. So in like one interpolation, you have like very discrete points and you're interpolating between the points.
Mm-hmm.
I guess maybe the axes on the interpolation for the non-interpolated data.
The axes here are indexing. They're not length or size of the plate. This is telling me I have 5 values here, 1, 2, 3, 4, 5 values, and 5 values in the y direction. It's not the actual dimensions of the plate. And then for each so at this first entry over here, y0 and x0, I have 100. And then at x equal 2 and y equal 2, for example, this point, I have 64. Now, what happens in between these two, right? So this is constant for this entire block, which is about, whatever, 2 centimeters by 2 centimeters, right? Whereas when you do interpolation, it's not necessarily constant. You're going to assume that it varies linearly.
Are you like holding the, are you adding a lot in between each point and that's how you get the smooth?
I'm adding a lot of points, yes. So when I switch from here to here, I create my interpolant, just like what we did when we plotted with temp points, right? So we had the discrete points, and then we created a lot of points in between so that we see how the polynomial is behaving. I'm doing that here, exactly that. Okay? So I create x new, I create a new length space of 100 points between 0 and 8, and another 100 points between 0 and 8, and that gives me more points in between. And then I plot all the interpolated values in between, so it creates this nice and smooth thing. So the axes here, the label on the axis, that's a good catch. These are just simply how many points you have. They're not labeled based on the size of the plate, because I'm using something called image show from Python, which just shows you an image without actual kind of fixing the axis. It's a little bit more complicated to create axes for this. I didn't want to get too involved in that, but this illustrates this idea. Okay? Does that answer your question? Good. We can talk after if you want. Okay, so next we'll talk about regression, which is the other side of curve fitting. The interpolation we said was useful when working with nice, clean, one-to-one data. Thank you. Oh, actually, keep it. Interpolation was good with working one-to-one data where there's a clear physical mechanism. When data is scattered all over the place, regression is the way to go. And the purpose of regression is to capture the trend of the data rather than the data itself. So I give an illustration here that you have a bunch of data given in these blue points. They don't lie all on, like, it's silly. It would be silly to connect them like this. That's like a foolish idea to do. Instead, you look at the trend that as x is increasing, the response is also increasing. Maybe it's increasing as a straight line or increasing as a nonlinear curve or a polynomial. That's up to you to choose. And the idea of regression is we want to put a model curve of our choice. We choose the model curve. Could be a straight line, could be a Gaussian distribution, it could be anything you want, okay? But you are trying to fit it into these points. Now, the way regression works, if you've learned regression before, the way this is done is we get the model curve. How many parameters does it have? So if you're fitting a straight line, you have two parameters, the slope and the intercept. If you're fitting a combination of logarithms and exponentials, maybe you have 2 or 3 parameters. Then you want to adjust those parameters, essentially kind of move it and twist it around so that you minimize the average distance between your model curve and the input data. That's what regression is doing. You're minimizing the average distance between your curve and the input data. And that's basic regression. Again, I don't want to teach regression here. I want to give you the methods to do regression analysis. If you haven't done regression analysis before, you should study it. Again, you can look at those on my lecture notes. There's about four or five lectures on regression. Really good discussion on regression. You learn it once, you'll never forget it. I guarantee you that. Did you guys forget my lectures on it? Okay, good. See, good answer. So okay. The first approach to regression, and that's where, you know, the basic scientist or the basic, person trying to do regression, like maybe someone from the humanities, they're trying to regress data from observation in a social study or something. They don't, necessarily know about complex exponential functions, etc. They just probably want to look at fitting a straight line because straight lines are easy, or just a quadratic curve. Those are well understood. So the simplest type of regression is to regress to either a straight line, a quadratic, a cubic, or a polynomial in general. And guess what? We can use polyfit to perform all of those types of regressions. And we're familiar with polyfit. Polyfit, you give it input data of input x data, which is the independent variable, input y data. And we used this last time, and we had a discussion about degree. If you want to do interpolation, degree needs to be equal to number of points minus 1. Anything less becomes regression. Anything less becomes regression. Why? If you have 10 points, you have 10 parameters to work with. Okay, so you can do an interpolation. If you want to do an interpolation, you want a polynomial or a model that has 10 parameters in it. But if you're trying to fit a model with 2 parameters, 2 unknowns to 10 points, you cannot do this with the same way we do with interpolation. You have to do regression. You have to minimize the error. You have to look for something else to try to figure that out. And so that's why it becomes regression. Degree is the degree of the polynomial. And if it is less than the number of points minus 1, then regression will be performed. So if degree is equal to 1, then you are doing regression to a straight line, assuming you have 1,000 points, okay, or 100 points. If degree is equal to, you will be doing regression to a quadratic. If degree equals 3, you will be doing regression to a cubic, and so on and so forth. So degree is the order, the highest power in your polynomial. So that's polyfit, and it does regression for you. So what we will do, we will apply it first to this data set that I talked about last time, height versus femur, that I showed you at the beginning of the lecture on Tuesday. So let's go ahead on Jupyter Notebook. And in your canvas, if you go under Files, Regression, there's a text file called height versus femur.txt. Height versus femur data.txt, I think. Okay? So let's grab that one. If I can find my way around here. Okay. so I do have the height versus femur here with me. So I will go ahead and create a new notebook. New notebook. And I will call it, I'll move it here, move the crest on. Okay, so we can import our usual boilerplate. So let's just come here, NumPy, etc. Did we have polyfit here? Yeah. Okay, so I'll just copy and paste this of the other notebook. And first, let me call it Fall 2025 regression height versus femur. Okay. And I don't need cubic spline. And I can do from NumPy import polyfit. Okay, if you want. And input data is equal mp.load.txt. And let's see, height versus femur. Okay, height versus femur. So let's print input data, see what it looks like. Okay, so I think, so it is two arrays stacked on top of each other. The first array contains the femur length, and the second array contains the heights of the individuals in centimeters. So if I were to do input data 0, it will give me the xi. So my xi data, or let's keep it xi, and my yi data is input data at 1. Okay, and we can do plt dot plot xi yi. Okay. All right, that's my data. Now, again, if you were to connect this with a straight line, it would look terrible. You shouldn't do that. Anytime you have scattered data connected, just keep it scattered like this. And you can do plt.grid to beautify it a little bit. plt.xlabel, femur length in centimeters, and then plt.ylabel, person's height in centimeters. Person height, person height in centimeter, or height in centimeter. Okay. Okay, very good. So I want to regress this now. We'll start by trying to regress it to a straight line. And it's really, really simple. I have my x data, my y data. This looks like it is a straight line. Agreed? It looks like it's following a straight line. So doing a straight line fit seems suitable. So I'm going to do polyfit, and we'll give it xi, yi. Now my degree is equal 1. Okay, so how many data points I have? I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 data points. Okay, so I'm in the clear. If I put degree equal 9, it would do interpolation and probably will crash. It will not converge because I have these two values here and these two values at the same x, so it will not do interpolation for you. But at least degree equal 1, I know we're not doing interpolation. This is definitely regression. And when I run it, it gives me two numbers. What are those two numbers? Those are the coefficients of the polynomial. This is, and remember, those coefficients go from the highest order to the lowest order. So this would be a1x plus a0. So this would be a1, that's the slope, and this is the intercept. Okay? Okay, great. So now I want to plot this, and to plot this, we can do it with polyval. So let's go to polyval. Let's import polyfit and polyval over here. And remember, polyval takes coefficients, takes coefs, and applies it and does the interpolation at some value. Let's say your femur length is, you know, I don't know, say you're freakishly tall. Your femur length is like 51, okay, centimeters. So it's going to predict a height of, well, that's not very tall, 175 centimeters. That's like average in America, I think. Okay, so that polyval, it does that, but I'm interested in really plotting this on top of the original data. So what I need to do is create new x values, like a linear space, or xi's, let's call it, or xi vals, mp.lin space. And I want to make sure I stay within the data. Now, regression, you can try to extrapolate with regression. What that means, go outside the bounds of your data. Okay, because you have a model that's just going to apply, you can apply it outside the data, but be careful. Interpolation, it's a no-no. Don't go outside the data. It's a bad idea. Regression, we can go outside the data, stay close to the data, but we can go outside it, and we should be okay, because it's a model of the data as you're capturing the trend. Hopefully it works for an extended range, because I doubt that, well, I don't know, maybe as femur length increases, heights are going to stratify, right? So it's not going to be a straight line all over, right? If femur length go to 60 centimeters, I don't know if people will get taller than 2 or 3 meters, right? Or it's very rare for that to happen. So my guess is that, you know, the data will stratify over here, and it's no longer a straight line. So it's a bad idea to do extrapolation. Still, you can do it. My lin space then is going to be from minimum of the input data to the maximum of the input data, right? So that's going to be 40 to whatever maximum data was 51, right? And I'm going to do 100 points. Now, this is a straight line, so it doesn't matter how many points you're putting, but that's okay. So plt.plot, and so let's take this again here. I'm going to put this here. And we will plot now, plt.plot. We want to plot the model. So we're doing xi vals. We're going to plot the model at all of those additional points that we created, the lin space. That will be through polyval, coefs, and xi vals, right? So I'm evaluating my regression model. I'm evaluating my regression model through polyval, giving it the coefficients we computed from the regression, and evaluating it at 100 points in between 40 and 51. And I'm going to do this as a straight line. Just do a straight line and make it red. And look at that, okay? Gives me regression. Okay, gives me regression. We can try a quadratic if you want. So we'll go coefs quad is polyfit xi, yi, and degree equal 2. What do you expect for the quadratic? Do you expect a high quadratic effect? So what do you expect the coefficient of the x squared term in the quadratic to be? Large or small? Almost 0, right? That's our hypothesis. So let's test it. And actually, we just print coefs quad. Okay, so it was 10 to the minus 3. Not quite 0, but a very small number nonetheless, or a small number relative to the other numbers, because that constant in that quadratic is 128. And so we can plot this as well. So we can go here and say, do another plot at polyval coefs quad, okay, and do it in blue. Well, it's almost on top of the red one, right? Except you see it's trying to lift off at the endpoints. So it's trying to come up here and trying to flatten out over there. Maybe that's what the real data actually looks like. They plateau at small and high femur length, right? So I don't know. Or actually, no, this one is going to keep going higher. So it doesn't plateau over there. That's basic regression. Okay? Polyfit is limited to these things. Polynomials. Okay, very good. Now let's throw a wrench in this. Now, I want to state something, and my students know how adamant I am about this, that I make a clear distinction between what I call linear regression and nonlinear regression, and what I call regression to straight line and regression to a quadratic, for example. In the context of computing, or in the general public, when you tell someone, oh, I'm doing linear regression, they will understand that you're doing, they will assume that you're doing regression to a straight line. That's not wrong. Okay? But from a mechanistic perspective, where you're building these regression models, even polynomials are also a type of linear regression, because the regression system of equations is linear. So anytime the coefficients of the model show up linearly, that will result in a linear system of equations for the regression. So it's a linear regression in that sense. So to avoid any of that ambiguity, I advise you to use words like regression to a straight line, regression to a quadratic, regression to an exponential model, and say what the model is. Ditch the word linear and nonlinear regression, and I'll give you an example here. So for instance, this model, a plus bx cubed, a and b, they show up linearly in this model, and the regression system of equations will be linear. So I can call this linear regression, although it's not regression to a straight line. So to avoid ambiguity, I say this is regression to a form of a cubic. This guy, this model, a cosine t plus b sine t plus c exponential minus t squared, highly nonlinear transcendental functions, but the coefficients show up linearly. And this will result in a linear system of equations for the regression. So we would call this linear regression, or say, you know what, I'm regressing to this model, sines and cosines and exponentials. This model here, alpha and beta shows up nonlinearly. This will result in a nonlinear regression model. Now, this model is nonlinear in sine and cosine, same there. But just be clear, say regression to straight line, regression to cubic, or regression to this model. Avoid any confusion. OK, polyfit cannot do this. Like, this is a very specific polynomial. Although polyfit can do polynomials, but it will do it for the coefficients in between, for x squared and for x. But what if you only want to do a plus bx cubed? I don't want the x squared, and I don't want the x. Or what if I want to do regression to this model? This is my polyfit cannot do this. Polyfit is strictly for full polynomials. Straight line, quadratic, cubic, etc. Fourth order, quintic, etc. And the question is, it would be really cool if there's a built-in utility in Python to do this, to do regression with arbitrary models. To perform regression with arbitrary functions. Okay? Arbitrary functions. Yes, there is, thankfully. And that routine, that utility from Python is curve-fit. Curve-fit is a general regression methodology. It handles both linear and nonlinear models for regression. It handles everything, really. And inside it, there's a nonlinear solver, because when you're trying to do a regression with a nonlinear model, the equations that you need to solve will become highly nonlinear. So you have to do an fsolve or root like we did before. So curve-fit does all of that for you. And it comes from scipy.optimize. You import curve-fit, and you use it as follows. Curve-fit requires at least 3 parameters. a model, the model that you're trying to fit, input X data and input Y data. Why? It needs the input data because it's trying to fit the model to those data. Okay. Now, what is model? It's simply a Python, the name of a Python routine that implements your model. We'll see this once we get to it. Okay. It's simply a Python routine that implements your model. Think of the residual functions that we implemented. When we called root on the residual routine, that was just simply a Python routine that computed something, right? So same thing here. The model that is being fitted, it should be implemented as a model, as a Python routine of the form model X. The first argument needs to be connected to the independent variable, and then a bunch of parameters, because your model will need to be fitted with A, B, or A, B, C, or you could have 15 parameters to it. You need to list those back to back over here. It must take the independent variable as the first argument and the parameters to fit as separate remaining arguments. Xi is the vector of independent variable entries, known as the known input values, okay? And then Yi is the vector of the known dependent variables. So that's Xi and Yi are given to you. Now, curve fit returns two numbers, two quantities. One of them popped or p-optimized or optimized parameters, parameters optimized, or the parameters from the optimization. How many ways can I say that? So popped or p-opt, these are the optimized parameter of this model. Okay, and p-cov, don't worry about this. This is a covariance matrix. We're not going to learn. We're not going to care about this. All we're interested in is this p-opt. So if your model has two parameters, p-opt is going to be those two parameters that are optimized to fit your model to xi and yi. Now, when I say fit, what do I mean? What am I trying to optimize? What am I trying to do when I say fit? We are minimizing the average distance between those points. So when you go and look up the signature, function signature of curve fit, it tells you this is called the least square error. So that's it. We're taking the average of the square of the errors or the distances between your curve and your input data. And you're trying to make the curve and adjust it to the best way possible so you minimize that average distance. All right? So now this curve fit in general performs, it will perform full nonlinear regression. So inside curve fit, if you look at the source code, you will see in there scipy.root, okay, scipy.optimize.root, and it's trying to solve a system of nonlinear equations. When those nonlinear equations are actually linear, it will still find the roots in one iteration. It will always find them when the system is linear. So it works for linear models and nonlinear models. It's really great. So you don't need polyfit. You can use it instead of polyfit, except you have to still program your model. All right. The first example we will work with is this one. 3 disease-carrying organisms decay exponentially in lake water according to the following model. So there's like some bacteria in one of the lakes, and they monitor these data usually. So if you're going to spend some time at a lake or swim, oftentimes you see alerts like don't swim, the bacterial levels are high, there's like algae activity going on. They measure, they take samples of the water every day, and they look at what organisms are there. So in this case, there's 3 disease-carrying organisms, and they decay. In other words, the population just kind of dies off over time according to this model. So population, those are the number of your bacteria, let's say in millions. And they decay according to this model. A, e to the minus 1.5t, plus B, e to the minus 0.3t, plus C, e to the minus 0.05t. T is time, measured in seconds or hours. In this case, it's given to us in hours. And A, B, and C are coefficients, are unknown coefficients. So now we have some data from measurements, okay, given T hour and the population of those 3 organisms. Let's call the organisms organism A, organism B, and organism C. And over time, the population, so at 0.5, at half an hour from the initial population introduction, there were let's say 6 million of those organisms. After 1 hour, 4.4, 2 hours, 3.2, and so on. After 9 hours, 1.1 million or 1,100 were left. So assume there's a unit over here added to that. Okay. Estimate the initial population of each organism given the following measurements. So now they're asking us to extrapolate, to go at t equals 0, what is the population of these organisms? Okay, what is the population of these organisms? And each one of them separately, okay? And in other words, they're saying at t equals 0, what is A, what is B, and what is C? At t equals 0, this is 1, this is 1, this is 1, and simply we have A plus B plus C, which are the parameters that we're looking for. So let's do this with curve fit. We're going to program this by hand because the data is simple. So let's do another. I have to create it here on this one. So create a new notebook if you want, or just, I say create a new one. So you have a lot of notebooks to, like say, where is my notebook? Okay, where did it go? Ah. So that was the old one. Hold on. Okay. So fall 2025, disease carrying organisms, regression. Curve fit, disease carrying algorithms. I'm just going to take this boilerplate from here, and from scipy.optimize, I want to import curve fit. Okay, so this is my scipy.optimize import curve fit. Okay, great. So next we need to input our data, so we can input the data just by hand. Lectures, 1 second. So we'll input the data by hand. And we are going to say that my xi data, which is time, is we have 0.5, 1, 2, 3, 4, 5, 6, 7, 9. Okay, so we have xi equal mp.array, and 0.5, 1.0, 2.0, 3.0, 4.0, 5.0, 6.0, 7.0, and then 9.0. Okay, that's our xi data. Our yi data is numpy.array. And let's move this here a second. We had 6.0, and then 4.4, 3.2, 2.7, 2.2, 1.9. 1.7, 1.4, and 1.1. Okay. When data is at hand, plot it to understand. plt.plot, x, I, y, I, OK. All right. This is our data. OK, it does look like exponential decay. So the model they're proposing looks adequate. There is some exponential decay. Could they have come up with something a e to the minus alpha t? Sure. But they wanted to try this one. Okay? They wanted to try this one. All right, so let's try to figure this out. The first thing is we need to define our model. So define decay model, I'm going to call it. By definition, this model is going to take the first, the independent variable, x, you can call it t or whatever, let's call it t. And then it needs 3 parameters, a, b, c. Just put them like that. You're going to be like, oh, how is Python figuring this out? It's magic. It's a miracle. Okay, Python knows how to do it. Just put it this way. Assume you're just evaluating this function here as a Python routine. What do you want? You want t, a, b, and c. Just program it this way. And then simply return a times np dot exponential of minus 1.5 times t plus b times np dot, times np dot exponential of minus 0.3 times t plus c times np dot exponential of minus 0.05 times t. That's it. Just return this. Assume that you're just writing a code that evaluates this model. Internally, Python is going to keep calling this, and it's going to give it t and values for a, b, and c, and it's going to check, is my error going down or my error going up? That's what it's doing. Imagine it's searching for different values of a, b, and c in a very smart way to find the best values that minimizes the error. And that's what it's doing. So you just implement it like that, and then we can now implement, we can now call our curve fit. Okay, there's my curve fit. 1 second. So we will call now curve fit, and like I said, we put popt and pcov, just put them like this, and call curve fit. Now for curve fit, it requires the f, the model, x data and y data, maybe an initial guess, a bunch of other things. We don't have to worry about that right now. F is callable. This is the model function. It must take the independent variable first as the first argument, and then all the other parameters as the remaining arguments, just as we did. And by the way, the docstring says this uses nonlinear least squares to fit a function. Least squares means it's finding the minimum sum of the squares of the errors, the distance between the curve and the data points. Okay, great. So we're going to give it, just say this is my decay model. That's it. That's all I have to do. This is my decay model, and xi data and yi data. Python is smart. It's going to go in here and say, this decay model is a Python routine. The first argument, I'm going to assume this is the independent variable. How count the remaining arguments? And then it figures out by itself that I have 3 parameters. Therefore, I need 3 nonlinear equations. I'm going to find those, et cetera, et cetera. And then let's print popt. So when you do this, you get 4 numbers, okay? And those are going to be in that order, A, B, and C, okay? If you swap the order, then they're going to be swapped as well. But this is the order they come in, and therefore, this is your model now. This you just did the fit. So let's see how the fit works, okay? We're going to plot this again. It's going to be plt.plot. This is the original data. Xi, yi, and then we're going to be OK. And then I'm going to create a bunch new data, xi data, and mp.lin space. And let's say we can go from min xi to max xi, and we'll put 100 points. Next, I want to plot my model now. Okay, so now plt.plot. I'm going to give it xi data, and then I want to use decay model, okay, and I'm give it xi data here. But now how do I pass the A, B, C? I can go popt 0, popt 1, and popt, okay, so popt 0, popt 1, and popt 2. Okay, so those are the ABC. And then when I plot it, it gives me an error. This is np.lin space. Okay, so that's my curve fit, the blue line. okay, plotted at a lot of points in between those data. Okay, and it is a curve fit. It does the job. But this is annoying here to have to do p opt 0, p opt 1, p opt 2, etc. There's a much smarter and cleaner way to do it. All you do is star p opt. What it does, Python automatically figures out that this is a list of numbers. I'm going to unpack it and split it as the arguments. Okay? Works every time. So now you can answer at t equals 0, A was 4, and B was 2.9, and C was 1.57 or 1.5, 1.6. Okay? Great. Let's see, I got 25 minutes. I can do two more things, a couple more things, before I let you go. Okay. This is another example where you got environmental engineers dealing with the impacts of acid rain, must determine the value of the ionic product of water, Kw, as a function of temperature. So they suggest this model, A over the temperature plus B log 10 of the temperature of water, Ta, plus C, Ta, plus D. So this is still a linear regression model. Well, linear in the sense that the system is linear because A, B, C, and D, they show up linearly. Although you have 1 over t here and log t and etc. You're given data, you do the same thing. You do the same procedure, and you can do the regression. So you can try that out yourself. I wanted to try this model because this is a nonlinear one. The following model is frequently used in environmental engineering to parameterize the effect of temperature in Celsius on biochemical reaction rates of some species. And it's given by k equal k20, which is the value at t equal 20, times theta, which is another parameter related to the temperature, to the power t minus 20. So that's our model. It has two parameters, k20 and theta. Okay? It has two parameters, k20 and theta. T and k are given to you, are the input data. So t is the independent variable, and k is the dependent variable. And we have some data at t equals 6. We got 0.14 rate per day, change or decay per day, etc., and so on and so forth. Okay? So we want to use curve fit to figure this out and to estimate the reaction rate at t equals 17 Celsius. So let's go ahead and implement this. Again, I'm going to create a new Jupyter notebook. Notebook. Fall 2025. Biochem reaction rates. So this is nonlinear regression or curve fit. Let's just call it curve fit. Okay. So for this, I'm going to copy and paste what we just did here. And copy and paste these guys. Are you able to catch up with me with the typing? You want me to go like a little slower? Okay. Okay, so our data is given by this, and let's do it xi and yi if you want, or ti, ki, whatever you like. So xi is mp.array, so that's my temperatures, 6, 12, 18, 24, and then 30. Okay, and then my yi data, which is, so this corresponds temps in C, and yi mp.array, this is going to be 0.14, 0.2, 0.31, 0.46, 0.69, and this is k per day, reaction rate per day. When data is at hand, plotted to understand, plt.plot, xi, yi, OK. I like this, xi, yi, OK. Okay, so it looks like an exponential type function, like a power law. Not necessarily exponential because you have this theta parameter. This theta could be the exponential number, 2.78, or it could be some other number, right? So we want to try to find it. Let's define our model then. Define decay. Oh, same. We're going to call the same thing. Biochem. I like the word biochem. It sounds like biohazard, like you're doing something very important. Like when I pass by the labs and they had that, hazard thing, and they have like the shower in front, like, ooh, I want to work in that lab. But then until there was an unfortunate incident once, I'm like, I don't want to go close to that lab. I like my computers here. So biochem rate or biochem model. Okay, so this is going to take, I'm going to give it temperature, K20, and theta. Again, just implement it as it is given to you. Return K20 times theta to the power T minus 20. That's it. That's all you got to do. Just do that. And then popped pcov is equal curve fit. And we will give it our biochem model. And we will also give it xi and yi. And then print popped. Oh, look at that. It found the parameters. It found K20 to be 0.35 and theta to be almost 1, just slightly larger, 1.069. So it's not quite the exponential, excuse me. And so we can plot this similar to what we did before. And we can do xi nu is mp.lin space from min xi to max xi. So those are the bounds. You can expand outside the bounds if you want. Not necessarily recommended. And I want to plot the original data as well. And plt.plot. And I want to do xi nu in my model, biochemical model for xi nu and star p opt, right? We don't separate, and we're going to do this as a dash dot red. Oh, look at that. Very nice. It's almost like it's been doctored. And that's how they create these homework problems, right? So they come up with a model, and then they generate data from the model, and we just give you the data and then ask you to reconstruct the model. Okay. Give you a second to catch up. There's two things I want to talk about, so no break today, like every other day. All right, so I'll ask you this, for those who are ready. How can I assess that my model fit is good or bad? Model good, model bad. How do we know? You said R, you mean the R squared? Okay, since you brought that up, will you tell us more about the R squared? Well, you got yourself in trouble. I'm not going to force it. It's okay. What is, like, how? Just give me ideas. The R squared. But why the error? Okay, the error between the red curve and the input data. Okay. But how can you tell the error is small or large? You have to measure it compared to something.
Yeah, compared to experimental data.
But that's the experimental data. So let's dig through this. So you're saying we take the difference, we evaluate the red curve at the experimental data points. We take the difference between the experimental data and the model data and take a norm. So we can do this. Okay, let's do it. Right, so what you're saying is, let's evaluate my biochem model at the input data agreed, at the xi data, which is the input data, and star p opt, okay, and compare that to the original experimental data. Okay, so we can take the difference. We can say this is yi model, okay, and then we can do yi model minus yi. Agreed? Okay. So that gives me an array, and then I can say, so this let's call this error. And then I can say mp.linalgebra.norm, right, of the error. Gonna give me 0.0065. It's meaningless, right? Because, okay, is that big or small? Nobody knows. So we need to measure this error relative to something. If we had different curves, different models, we would say, well, the error compared to the error with this curve compared to the error to that curve is smaller, but still you're like, okay, I need a gold standard. What is my gold standard? So now we go back to the R squared. So the R squared is computing this error. Okay, it's computing, I'm just going to come back, because you're correct. That's the right answer. So the R squared is computing this error, but it's also comparing this error to a gold standard. What is the gold standard? If you took numerical methods with me, you better know the answer. But I know you're being quiet because you don't want. Okay. No. If you're given, remember when we used to talk in class, when you're given data, what is the simplest statistic you can give about the data? The average. So the R squared value is telling you, I'm going to compare the error of using this curve to represent the data compared to only using the average to represent the data. That's the best we can say, because regression is a statistical tool. And the idea is, if you're given data, what is the simplest piece of information you can give about the data is the average. What's the average grade in the class? How much on average did we spend last month? That's the simplest statistic, the most common statistic someone can give about data. So if you did not fit a curve, but you were to explain the data, you would give the average. Now we have a curve. Is the curve better than the average? That's what the R squared value is doing. That's what it's doing. If it's better than the average, it's going to get closer to 1. If it's about the same as the average, it's going to get close to 0. Okay? I have a full lecture about that in my numerical method. So I'll summarize it here real quick. I'll give you the formula. And so this coefficient of determination, this is what it's doing. It's comparing the error based on the mean, the error based on the curve, over the error based on the mean. Okay? And so if R squared is 0, is close to 0, in other words, you did not think about it intuitively. Don't remember 0 and 1. Think about mean compared to a curve. If you're not improving on the mean, you have a bad fit. Then just use the mean as to represent the data. If your curve is going to be better than the mean, then you're going to have a good fit. And so I'll give you these two visual examples I used to give in like exams, etc. So this is some data in yellow, and this is the average of these data, minus 0.02. Okay, I'm asking you, draw a regression line and tell me if this is going to be a good fit or a bad fit. What is the R squared value without computing anything? Forget the question 2. Okay, forget question 2. So good fit, R squared is 1. Bad fit, R squared is close to 0. So for these data, what is the regression line? Yep. You did this. It's going to be like on top of the average. Okay. So ask yourself, does my regression line improve on the average or not? No. It does not. So it's going to be a bad fit. So in this case, R squared is going to be very close to 0. Okay. This is the actual regression line. Its formula is minus 0.0031x, and the R squared is 0.00005. What about these data? That's the average, 7.531. And we're going to put a line, a regression line. What do you think the R squared is going to be? Closer to 1. Why? Because we've improved significantly over the average. Okay? Next time you think of R squared, is my curve a better representation of the data than just using the average to represent the data? If it is, then you're going to have a good fit. If not, you're going to have a bad fit. Worst case is when you're in purgatory, like in between. You're like, I don't know if it's a good fit or like a bad fit, right? And so those are situations where you have to assess in an individual case. Maybe the best you can do with certain disciplines is a 0.6 R squared value. Okay, maybe that's a really good fit in those cases. Then you take that and say, yes, this is a good fit. Okay, the formula, this is the formula for the R squared, so you can easily implement this in Python. You have ST, which is the error based on the mean. So those are your data minus the average value squared, and then the data minus the values from the model. And this gives you the R squared value. I have 10 minutes. I want to cover just two more routines, 2 more tools in Python, and hopefully do just one example. Okay, and this is numerical integration. So this is going to be important for your project, okay, because you need to use both of these. So oftentimes, we need to do numerical integration of either analytical functions, like integrate e to the minus x squared from 0 to 5, numerically. If you know the function continuously, you implement it as a routine in Python, and then you can use scipy.integrate.quad, quad for quadrature. That's the numerical technique to compute areas under a curve. So scipy.integrate.quad calculates the integral of a known analytical function between a and b. So you just give it the function name, or this function name is similarly a Python implementation of a function like we did previously. The first argument is always the independent variable, or x, and it would do a calculation for you. But when you have discrete data, you can't use quad. You have to go to NumPy, and there's only one routine in NumPy that does this and does a good job. It's called TRAPZ, or trapezoidal rule. And that trapezoidal rule is a discrete way to compute integrals. It's essentially summing up all the y values and multiplying them by the spacing. So you compute, you segment the data, it segments the data, and you compute like small areas under the discrete data to give you an integral. Okay? If you can spend a few extra minutes with me, I'll give you the 2 examples and we'll make them up. So we will start with, because I have a hard stop today on the tools. We need to start on ODEs on Monday. So I would appreciate if you spend just a couple more minutes with me. If not, that's fine. I'll continue by myself, and I'll put it on. I'm going to put it on YouTube anyway. Okay, so let's do first quad. In your project, you will use both. Fall 2025, numeric integration. All right, so let's put in the boilerplate here. NumPy, matplotlib. I don't need curve fit anymore. And from scipy, import, from scipy actually dot integrate, import quad. And okay, so let's say we want to integrate def my function given x, and I want to integrate p.exp minus x squared plus mp dot cosine x. Okay, that's my function. So to integrate to get the area under the curve, we simply do quad, and you give it my function. And let's say we want to integrate it from 0 to 2.1, right? It gives you a number and a tolerance error. So this is a very accurate value. The error is 10 to the minus 14. That's a relative error with iteratively. And so, you know, that's how you do it. Just quad, analytical function, you're done. For numerical, for discrete data, if you go on your let's see, in your canvas, there's a directory under files called numerical integration. It has data for CO2 world emissions .txt. Okay, so let's get that. CO2 world emissions, or CO, just input data, is mp.load txt, and then CO2 world emissions. So grab that, download it from Canvas, and put it next to your notebook. So let's see what it looks like. Okay, so it's two columns, year and CO2 emissions in metric tons. So my XI data are going to be the first column. So like we did last time, this is input data. Oops, input data. And we were going to do the first column. And YI is input data. I'm going to take the entire second column. So let's plot it. plt.plot xi, yi, OK. All right. So on the x-axis, you have year. And on the y-axis, you have worldwide emissions in metric tons. You know, 1985. 1990 when I was born. No, I wish. And I'm still a millennial, though. So, and then, you know, it kind of flattens out, then goes up, and then comes down, etc. And the question is, what is the total world emissions from 1960 to the end? Okay, just compute compute the integral of these data. Very simple. numpy.trapz and p.trapz. And trapz takes yi first, and then you give it xi. And then it gives you a number, 232.9 metric tons of CO2 were emitted by the world from 1960 to 2015, whatever. Okay? Very good. Actually, I finished ahead of time. Okay? Well, thank you. Godspeed. Happy weekend. I'll release the homework. I'll release the project today, tomorrow, and I'll figure out how many days you guys will need.